So a few seconds for people to log on. So, hello, welcome to our webinar, working with a digital version of a chip to improve performance. And we're sponsored today by Ascenz Marorka, a company that provides digital technology to improve fuel efficiency and reduce environmental impact in shipping. My name is Carl Jeffrey from Digital Ship in London, and we've got speakers today from Vessel Performance Solutions and Ascenz Marorka. So the digital version of a ship, that's commonly known as a digital twin or a digital ship model. And we're going to talk about how this can be used to improve vessel performance and other areas of maritime operations, including technical management, commercial management, and daily operations. These digital twins can be used to find ways to reduce fuel costs, save vessel time, and make better operating decisions. We hear this term digital twin very often, perhaps too often these days, so it gets quite hard to keep track of what it actually means, but hopefully we're going to have a clearer idea by the end of the webinar. So we're going to hear first from François Hanat. He's Head of Products and Customer Success with Ascenz Marorka. He's based in Paris. His background is in digital technology and innovation. He formerly worked at Cap Digital, a non-profit organization that supports digital technology companies in Paris. And he was lead analyst for AI technologies there and then operations manager. And we're going to hear second from Kristian Bendix Nielsen, who's director and co-founder of Vessel Performance Solutions, joining us from Copenhagen. VPS was founded in 2014 by specialists in naval architecture and data science. And Kristian previously worked as a vessel performance analyst and as head of hydrodynamics department in Maersk Maritime Technology, which was the engineering department of AP Moller Maersk. He's got a background in vessel performance analytics and has developed many analytical tools and algorithms for analyzing operational data from ships. Ascenz Marorka and VPS are related in that in February 2024, Ascenz's mother company GTT announced the acquisition of VPS. So we're going to have two talks of about 15 minutes, then there should be plenty of time for questions. And you can put your questions in the Q&A box at any time, but we'll take them at the end. And I'd like to invite François to start his talk.
Sure. Thank you, Carl. Thank you, Carl. Good day, everyone. Really happy to be here with you for this webinar. Maybe just a few words regarding Ascenz Marorka and VPS. As Carl said, we joined forces a month ago, and the idea is to provide technologies for the shipping industry. So within both Ascenz Marorka and Vessel Performance Solution, we leverage data collection, being sensor or manual data, artificial intelligence, machine learning and data analysis, and of course expertise, being both in naval architecture, offshore operation, LNG as well, with our mother company GTT. And the idea is to deliver a platform to support the shipping performance with data validation, decision support system, and support from our experts for advanced needs. So really happy to join forces with Vessel Performance Solution and Ascenz Marorka, and we think that we propose a very comprehensive solution, and we present today how we can help regarding the shipping performance. Just to give you a small infrastructure description on how we can support and build ship models and put them, set them in motion. The idea is to acquire data. So the first step, of course, when you have a ship, will be to use the manual data from the ship, so the moon report. So for this, we have solutions that called the light reporting that allow to gather all those data from the ship. Is the first level, and it's crucial. And this one, you have to do it in order to monitor the performance and manage it, and also for the regulation. For some ships, it's also possible to install and acquire sensor data. So we have also solutions to install acquisition system on board the ships to acquire sensor data. So at higher frequency, when it's possible for maybe longer charter contract. And we can gather data from multiple sources on board. So navigation system, alarm and monitoring system. When it's this, we can also get the reports from the crew, which we will pre-fill from the sensor data to save some time for the crew. But in both cases, the idea is to transfer this data securely to shore in our online platform where we'll propose different tools to assess the performance of the ship, meet regulation requirements, also weather routing module that is embedded in the platform, and many other modules. I will not describe all of them. The purpose is also afterwards, when we look at ship models, we also look at the data. We also propose APIs to feed the data, either within internal teams of the company to dig into the data, to conduct more advanced and specific analytics. But you can also share data with your ecosystem, so your customers, your partners, securely, because data can really feed and nurture relationships with your ecosystem. So what is at stake, in fact, when we talk about ship models? The challenge is really the cost around the shipping. So today it's mainly the fuel cost. So this is estimation from the IMO. So the annual cost of fuel is estimated around $100 billion USD. And in fact, when we look at each percent of savings you could bring, it's very quickly leads to actual savings, in fact, and this is only for the fuel. As soon as we say 1% of savings per ship, by taking different hypotheses listed here, but it directly will give you a 10 to 17 K USD per year per saving. So this is for 1%. So the more you optimize, of course, the more value you can generate. And this fuel cost, or for today, but now with the new regulation, especially EU ETS, the cost of CO2 emitted is not yet included. So you have also to include the savings in terms of CO2. So the purpose is to see how digital twins or ship model, indeed there are many words around this, but how those digital twins can help tackle this potential of savings for the shipping players. So what we propose for this webinar is to illustrate you some technical solutions and to illustrate them with use cases on how we can leverage those ship models to tackle the potential savings we just mentioned. So 3 steps: the performance management, which will be more the monitoring, the trending, benchmarking ship between them, and the feedback loop on the wide fleet level, and on the long term to have a continuous performance management system for technical teams, but Kristian will present this to you very well. Second step will be a better planning. When you plan a commercial operation, from the planning phase, really a huge level of savings can already be guaranteed, or let's say money loss can be reduced just by using the ship models to make better decision with tools to help making the decision-making process from the planning phase. So more, to put it quickly, for the commercial team, in fact. So how we put those ship models within the hands of the commercial teams. And then when the ship is leaving the port, now we are at sea, and now it's the live advice. How can ship models can support navigation operation at sea? And here it's really a live AI-driven advice for the ships that will re-update based on new weather forecast, actual ship conditions, in order to give advice to the crew. So performance management, better planning, and live advice. This is the menu for this webinar. And I will let Kristian take the hand on the presentation to start with the performance training. Yes, Kristian.
You're on mute.
Thanks, François. I'll just take over the control of this and start explaining about how we do the performance trending, and also how we use the digital twin in analyzing the performance of the ships. So, of course, the general performance management cycle is about monitoring, managing, and optimizing. But the fundamentals of all this is the ship model, which I'll go into a little more detail and explain how we utilize this and how we use the ship model to detect how the ship is performing, and thereby give decision support. The fundamental parts of the performance monitoring is related to the hull and propeller performance, because that's really where The biggest deviations in performance is seen over time, how the added resistance of vessels increases, and how you can manage that using the digital twin. So I've made a short illustration here of how we utilize the digital twin and how that is used to predict the vessel performance. So when we get data from the ships, you can normally determine the propulsion power of the ship either with a torsion meter or using the main engine fuel consumption, and somehow converting it into the power that's used for the propulsion. And at the same time, you have the ship's speed, which is normally obtained using the speed to water. So correct for the current to see what speed the ship is making good, and thereby how much speed you get from the power. But the measurement from the ship will normally include the environmental impact. So we do a weather correction of this environmental impact to get a calm sea prediction of what the propulsion power would have been if it was in calm seas condition. And that's done through modeling of wind and waves and also seawater temperature. And often we utilize AIS data and the hindcast weather for this, because this is the most accurate methodology of applying it. For all the ships, we have a baseline model, which is obtained normally during sea trial. So that's the condition of the ship in its prime. So when it's delivered from the yard, and when we have measurements, and we have a baseline for the ship in all conditions. And the offset between the baseline and the measurements is the added resistance. So the added resistance here basically determines what the potential of the ship, or first of all, what the fouling has been, of course, of the ship, and what the potential if the ship is brought back into the condition when it was firstly delivered. So this added resistance can be trended over time and can then be used to make decision support, of course, on what should be done to the ship, but also to do more commercial decision support, as I'll get back into it. So when we trace this added resistance over time, we can see that it grows over time. Normally it starts around 0 when it comes out of dry dock, and then it grows over time. And between cleanings, hull cleanings or propeller polishes, you can sometimes see improvements. And then you can link that with the data, of course, and see how it grows. And you can use, of course, this trending, first of all, to determine how the vessel is doing right now. So you can have a good speed and consumption estimate of the ship, how it's doing right now. But you can also identify what is the potential if the ship was brought back into its best condition. And finally, of course, you can use the trending to determine what is the quality of the paints, because the slope of these predictions will give you an idea about how well the paint is performing over time. With this little animation, you can also see that we try to highlight the idle periods, so they can be enabled. They will be enabled here. So you see that the red marks here is when the ship has been idle, and sometimes you can see a good correlation between the idle periods and then, of course, an increase in dry dock, depending on where it's been idle, how long it's been idle, and of course the conditions around the idling, especially of course the seawater temperature. So this is sort of the link between the raw data, the ship model, and then the performance side of things. We link it, of course, with the main ship events, so the dry dockings, the propeller polishes, hull cleanings and retrofits, and of course the ship operations side. So all this will give a good estimate of what's the potential of improvement of the ship in the condition I'm in right now, but it'll also give decision support, of course, to commercial decision support, either to a planning of a container network or for transfer shipping for bulkers and tankers, help give estimations of actual fuel costs. I'll just try to move on here. So when we look, one too many here. So when we look at the overall view of a fleet, well, then we can use this assessment of the added resistance on the individual ships to determine on a fleet level what ships are doing well and what ships are not doing well. We will come back a bit later to this mix of high frequency and new data, but generally, of course, if you have high frequency data and sensor data systems, you can determine the added resistance with a better certainty, and you can enrich the new data with a more certain predictions, but it also the fundamental methodologies works on both data sources. The example we have shown here is an illustration of how to get a fleet overview. So this will show in months since dry dock and added resistance. It will show the fleet composition and show how high the added resistance is for each ship. So somehow it will show the offset of each ship compared to its baseline. And when you link it as a function of the period into the dry dock, you will of course quickly find out that you have a decay of the fleet in average, and you will have some ships that are doing bad, where you in average have a high added resistance, and some ships that are doing well with a low added resistance. So the idea of the fleet overview is to give you a quick access to determine what part of your assets, what part of your fleet should be given special attention. Where should I focus my efforts, and which ships should I do something about? We also have other modes of displaying the data. This is with the big bubbles, and the bubbles here indicate how much is the monthly fuel consumption of these ships. So if there's a link with a ship that is lying up here with a high added resistance, but also with a big bubble, it relatively speaking is using a lot of fuel consumption, and therefore you really need to focus on it. Of course, if it's lying up here with a high added resistance, but at the same time is idling and not using a lot of main engine fuel consumption, well, then it's not, of course, so necessary to do something about it. But if you plan to activate the ship soon, well, maybe you should think of cleaning it when it's looking so bad. So that's one of the things we can help clarify. We of course look at the trends, the analysis, and we also have these plots based on the paint types. So a very important part of this trending can be linked to how the different paint types perform, and thereby how what's the quality of the paints that has been applied, and of course fundamentally also the quality of the dry docking that's been done. And you can link that with the operational data and see if certain paint types performing better or worse compared to how the ship has been operated and how the performance is of it right now. I'll see if I can shift this. So what we do is we use the noon and outer-log data, and together with the ship model, of course, to create the short and long-term performance assessment. As I say, a very important part of this is just to determine what is the current performance of the ship, what is my speed and consumption tables, and how can I then being able to use that commercially in your commercial decision support of the vessels. But of course, it'll also give you technical advice and technical input to what should I do with my assets. Should I do some cleaning, or should I do something to work and improve my assets? And finally, it's of course also give some benchmarking between the assets of the fleet. So which ships are good and which ships are bad, which ships are having a high consumption compared to others. It's of course fundamentally the performance management. It saves time having things systemized and having a system that does this. It is of course possible to take the numbers out themselves and generate and work with that. But having it put into a system, a performance system like this, will make it a lot easier to work with on a daily basis if all these things are integrated and the algorithms and the way of analyzing is unified. And finally, of course, you can help save money by determining and giving decision support on what should be done with your assets, and identifying the bad assets, the ones with high degrees of fouling or with poor paint types, and finding out how to optimize it. So fundamentally, it will give you a more cost-efficient performance desk. It'll optimize the composition, because you can find out which of your assets is doing well and which is not. You can improve the plans, so the set plans, for instance, for the vessels, if you have bad rating. And finally, there's of course all the regulatory compliance with it. You can find out the link between bad rating and what you should do with it. We also have an EU ETS framework now in place, where you, of course, on a voids basis, often have to determine these CO2 costs and their allocations, and all this is handled in a systematic way if you manage that properly. Let's see. So what I'd like to address as well is the ability to add the crew into the loop. So one thing is that most of this performance management is, of course, based on the ship having to report data into a system. It's probably less than 10% of the world fleet that's covered with a high-frequency data system. So at least for 90% of the world fleet, you rely on data reported by the crew. But if you never give the crew access to finding out what we do with the data or how we analyze it or the importance of the quality of data, you will not be able to improve that process of the data collection. I have to say, of course, the compliance side now has put a lot more focus and a lot more requirements to the data collection side. But involving the crew, we find is key for this. The crew is not normally responsible for the hull performance in general. That is, of course, decisions made in the office. So in general, what we do recommendations that you do fairly frequent propeller policies, and that also allows you to monitor the hull, do inspections of the hull at a relatively high frequency, and of course you can couple that with the performance monitoring and the data you get back from the ship, and see how well does it correlate. Does the ship look foul, or is there slime on it? And you can correlate that, of course, with the data and analytics. But going back to the crew, they have a key role, because if they're not given insight into what the data is used for, or the quality of the data they report, they will never improve. So we find it very important to give the crew a feedback into this. And especially for the regulatory side, now that the data, the frequency of which the data is verified by the verifiers has increased a lot, because many have these online integrations where the data is fed daily to the verifiers. Well, giving the crew feedback on that will help them rectify problems with the data and identify problems on the compliance side a lot quicker. So this is another big advantage of the way that the ships can work and give feedback to the crew, is that if you allow them to get access into the compliance and the validations of the verifiers, you can sort of build a self-learning loop into the system and allow the ships to get you can say, to take more leadership in the reporting to the verifiers and the compliance side. So we definitely find it very important to involve the crew in that. Now, I'd like to come a bit into the planning side of things and show a couple of examples. I don't really know how I can leave this. No. Okay, anyway, the planning side here is that we have a couple of modules that I'll introduce. I'll start by explaining how the scenario simulation works and how that can be utilized to get better cost optimizations of the voyage. So using the ship models for commercial optimization of things. So the scenario simulation is a module which will help simulate the commercial voyage bits for the loading and discharging, of course, and then and especially for multi-leg operations, this is quite tricky if they do several loadings or several discharges and finding the balance. And normally, when you do the commercial optimization, you look at big eco voyages and the full speed. But when you look at it into more depth, well, for instance, the draft dependency or the weather factors comes really important when you do these commercial optimizations. So that's all what we built into the scenario simulation tool, which allows for much more detailed analysis of commercial voyages and avoiding the sort of simplifications that's normally done in commercial voyage estimations. We'll have some examples. I'll show something on TCE optimization, and François will present something on LNG cargo constraints. So let's see if we can get this to shift. So the scenario simulation basically works in that you define a voyage from A to B. You define a ballast leg and a laden leg. Here the laden leg is illustrated from South America to Belgium, and then you add the constraints of the voyage, of course, about ETAs and laycans and so forth, the speed limits, and with the associated parameters of the voyage. So the voyage constraints itself, the cost of the vessel, the cargo commission or cargo payment, fuel types, blah, 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 the merge and so forth. Well, with all that input, you can do a full simulation of that. And what the tool here does is that it puts it all together and then simulates a wide range of combinations of speeds to ensure that you get the most optimal out of the voyage. So actually, it is presented this way that you get an eco speed and a full speed estimate, and then the result of this simulation will be a best yield. And in this case, you can see that the eco and the full speed is 11 and 14 knots, but somewhere in between, that there's a simulation around 12.4 that gives a better yield, and that is and thereby better TCE. So you can see these numbers here. I'll explain them on the next slide. But fundamentally, it examines the full range of different speeds and drafts, and thereby find the optimal combinations. And as I said, a tool like this will be much more advanced than what is normally used in voyage management systems, because there you have a fixed weather factor, and you also have fixed drafts. For instance, either you are ballast or you are laden. But that is not always the case, of course. If you have a trade with a heavy cargo, you have a higher draft than with a light cargo. And especially if you have multi-leg voyages, where you can't always assume that you're going on the full laden draft, you will also have intermediate drafts. So a tool like this will help improve the decision support commercially on the voyages. So here, to drill a bit down into it, as I said, there was the two charter party full or eco speed estimates, and what the solution came up with was a best yield, which was a speed somewhere in between. So you can see there's a slightly higher TCE. There's a slightly daily earning in this, $705 per day compared to the full speed, and approximately $1,000 better on the eco speed. Now, on the total cost side, the eco speed will always be the lowest because it takes the most time, and the result of the eco speed voyage will normally be better. But you will also spend more days in that. Let's see if I can get it to work. So normally in this example, the eco voyage here took 37 days, while the best yield was estimated to take 34 days. So even though you finally make more money on the eco speed, well, on a per day rate, analyzing and optimizing it for best yield will give you a better commercial voyage. And of course, this will also give a different impacts on the CII or other compliance parameters, which is of course hard to quantify. You will see how it impacts on the year to date, and again you will see that you get the best and the lowest AER on an eco speed voyage, but often there's of course a trade-off that you can remain within the same boundary of the CII, and therefore you get a better commercial voyage out of this, if you of course don't jeopardize and violate the rankings of the ship. So this is another example of how you utilize the ship model together with more advanced algorithms for simulating voyages, and can use that for commercial estimations of voyages. So I think I'll hand it over to you now, François. Yes.
Yes.
I think I'll just exit here.
No problem, no problem. I will take it from here. Thank you, Kristian.
Thank you.
So after the scenario simulation, we wanted to present you another use case of how a digital twin can be used. This one is specific to the LNG segment. When we are talking about LNG carriers, they have a very specific aspect, is that the cargo is also the fuel. So when you plan a voyage, you have also to anticipate for each scenario in terms of cargo, what will be the context. For an LNG carrier, they will load a cargo with a given temperature, and they will have, which is cryogenic, so minus 460 degrees. And when they will discharge the cargo, the arrival terminal will have some constraints, saying the cargo should not be too warm, should be in the limited scope of temperature, or pressure, depending on terminal. But it's really something interesting with LNG carrier. As the cargo is also the fuel, as soon as you plan, you have also to anticipate what the cargo will do. And in fact, it's not what the cargo will do, is what you have to do to keep the cargo in the correct discharge requirement from the terminal. So from this, we have to model, to extend, in fact, the ship model. So we keep, of course, the propulsion model. We have also the hotel load for the diesel generator. LNG carriers, they have a gas combustion unit to burn the extra boil off. And more, they have some active system, reliquefaction plant, subcoolers, etc. This is to take the gas, evaporated gas, we call it the natural boil off, to take it, and as it's too much versus the engine's requirement, let's reliquefy it by, in fact, consuming additional fuel for the DGs, but in order to save the cargo. So in fact, the purpose of this ship model is to be called with two things: a discharge, let's say an ETA first, because LNG carriers in general, they have to respect very defined, precise slots at discharge terminal, and they have also to respect this cargo constraints at the discharge. And that was a use case we did for a charterer. They wanted to help their commercial team to identify what will be the consequence in terms of loss of cargo, depending on two things: the speed profile. So on the same route for this trade, the US-France, on this route, test different ETA that led to different speed, in fact, or average speed here, and also different temperature constraints at the arrival port. So that's the heat map. And the idea was also to check. So you see the different temperature tested, and to test it based on the equipment available on board. So in that case specific, if the reliquefaction plant was working or not working. And in fact, it allows them to build some heat map like this to know, based on a specific speed I choose, so specific ETA slot and a specific constraints, should I fight for negotiate with the discharge terminal for a slightly warmer cargo? In fact, and are you fighting for 10 cubic meters or 100? And the extreme value of those heat maps in terms of cargo value represent 300K USD. So of course, all terminals do not present the same flexibility. But this is an example where you combine the propulsion model with, in fact, a thermodynamic model based on the change of thermodynamic state between departure and arrival. And what do you do at sea? Do you use an active system that will impact the cargo and to have a consequence either in terms of evaporation? This is for the crew to know how much they have to evaporate to meet the requirement, or for the planning team, in fact, what is the order of magnitude, the sensitivity around this thermodynamic property, which is very hard to manipulate and to do a computation by just by the head without tools. With this tool, this ship model, you can really call it with different speed profile and thermodynamic constraints. So it's an extension specific for LNG, maybe not interesting for all of you, but this is the typical things that Ascenz Marorka and VPS are doing and will continue doing to combine the propulsion ship model with also LNG models when it comes to this particular segment. The last part of the presentation is to mention what we can do when the vessel left the departure port. And here with the live advice is to see how we can support the crew to save fuel. Two main use cases. The first one is the machinery. So on board, the ships in general have multiple diesel generators, so auxiliary engines, to deliver electricity for the hotel load for the ship. When we say this, in general, you have multiple groups of engines, not the same maximum power, not the same MCR. And each individual engine will have its own specific fuel oil consumption or efficiency curve. And the idea is to have those efficiency curve to look at every moment. Based on what the electricity delivered currently by the DGs, is there another way, a better way to generate this electricity, but that will save some fuel? And that's the use case which is here. When we say the left section, the red part, at this moment, we highlight that there is a deviation or at least room for improvement for the DG operation. At that time, the ship has the three DGs running. By looking at this, the short team, if the crew missed it, because sometimes we have system on board that can help the crew, but if you do not have a system on board, as said Kristian, most of the ship have only non-report, but from there, you can also help the crew to say, be careful, please review if the DG usage is efficient. Assessing this before and after, so they turn off one engine, and the estimation conducted with the user of this module was that for both maintenance cost, because having an additional engine will lead to maintenance cost, so operation cost, plus the fuel cost. So if you take into account both maintenance and fuel cost, it leads to a $350 per day that can be saved or that are lost in case you are running too much DGs. So this use case is really on a with a specific user. And of course, the purpose is to monitor that on the long term and to extend this to so if we do not have a system on board, also to a system to warn the crew automatically to review the DG implementation. Of course, when it's possible, sometimes when you're maneuvering or for specific actions you have to do, or in high risk area, you may be outside the operation, the optimal ranges, no problem. But in general, there are some good room for optimization regarding the machinery. That's one use case. And for this, each individual engine has its model, and you have to add on top either a layer to estimate if it's following some basic maintenance rule, or if really you add on top an optimization engine that will look for any output electricity you request, what is the best implementation based on the different group of engines and individual model, the efficiency curve of each engine. And you have to run that continuously. So it's really, the message is to put those advice in motion. It's not only calling someone who will assess, it's the tool that has to continuously assess it and give the advice, give the alert to take mitigation action when possible. So this is for the machinery optimization. Another use case is something that was launched last year, or maybe a little more now. It's the weather routing module. So it's a very common tool for the shipping industry, but it's really something that you have to look at and that you can feed and nurture with ship models. The ship models, in that case, will contain the propulsion aspect of the ship, but we have also to consider the impact of the weather condition, and not only the height of primary wave. You have also to take into account the direction, the relative direction of this one, also frequency of waves versus the hull. So it's an extended ship model on which you will add on top the impact of weather to take into account the additional consumption and the impact on how you will conduct the operation afterwards based on some weather forecast. And same for machinery. It's not only to get one passage plan proposal, which by the way have to be efficient, but first it has to be safe. So you have to respect also multiple constraints, being the restricted area, the traffic separation scheme. You can also avoid specific area, so some passages, some piracy zone, etc. So it's an optimization algorithm that regularly you will feed with new information. Of course, new weather forecast, it's always changing. And of course, what the ship actually did, because for those systems, being with noon or with sensor data, you know exactly what the ship did, and you know where the ship is. And potentially there may be some deviation, specifically where you have a harsh weather condition. But really, this optimization module, configured with the ship model, enhanced with the weather impact on the ship performance, that you will set in motion regularly. You can update once a day or more based on the availability you have to assess the update and potential new routes that could emerge with the new weather forecast and with new savings. It's really what we are achieving, a tool fed with live data from the ship and the weather, and also with the actual condition from the ship to always look at potential on the planned route. Is it still okay? For instance, if you have a maximum wave height at 6 meters, if with the new weather forecast, it's now 7 meters, maybe the master will want to rebuild a passage plan. So that's the first rule. And the other is if you are trying to save fuel cost or daily cost or just distance, you can always look in parallel. Is there a new optimized route that should be considered because based on those new parameters, actual and prediction, weather prediction, a new opportunity appeared. So on top of this module, this is some use case we had with the team. Because on top of this system, which is a standalone, we also have a fleet center that can support masters into defining so safe and efficient passage plans. So this first use case was a combination to avoid a storm. So to put it shortly, is the rum line versus the grid circle. To avoid a storm, a competitor provided a rum line route, so it's extremely safe, but it's really not efficient. While in fact, if you try to always respect the maximum wave height set for this ship, which in that case was 6 meters, is there an opportunity, an alternative that is more efficient? And in that case, yes. So it's really, let's not take the simplicity with Rumline. Let's leverage all this information we have today, and it's really powered and driven by the accuracy of the ship model to always meet the safety features, the safety limits of the ship, but to also keep on top of it a target of fuel savings, so fuel or overall cost, if you have also this to take into account. So here it was this case was so roughly 40% saving for this one, because indeed the rum line is never rarely the good approach. Another case, with the deviation point set by the master, in fact, within the Atlantic. So you can find alternative routes from so the routes planned from the vessel in green and the one that we planned in yellow, so slightly more GC as well. So in that case, less percentage than the previous, but still percentage of savings that can be leveraged. And again, here you see it's really a matter of respecting the constraints. So always the RTA, required time of arrival, and if any deviation point, and potentially safety specific areas such as the NAVTEX, when you want to avoid the NAVTEX. This specific case, a crew decided to deviate by the east, while in fact it was possible to deviate always by respecting navigational constraints by the west, and by, in that case, very short voyage to have a very more interesting in terms of fuel cost route for this deviation by the west. So always challenge, and in fact, it's a matter of giving the right tools to the people, because we may want to reuse a route from that we use from the past, but always check if there is a possibility with all this power driven by accurate ship models and also tool we put on top to help making the decision with the optimization engines. That was the last use case, and to leave time for the question, sorry, took some time. The idea is really to try to save fuel and CO2 by leveraging those ship models. And as we said, on the long term, before the commercial operation and during the operation. So feel free if you want to engage the discussion, now or later, regarding how to leverage the data that are available, manual, of course, and potentially sensors. And as said, Kristian, it's possible to work clearly and smoothly with both, and to find a good methodology to implement based on a specific segment you have. from the shipping industry based on specific contract types. You may not have the same flexibility. So we are open to pilot such solutions, to demonstrate and pilot such solution on your use case, and to potentially adapt if your use case is in fact a silent issue that a lot of people have. We're really looking to adapt and make them make our solutions improve for this. And to complete, really, that's why Ascenz Marorka and Vessel Performance Solution teamed up, is to deliver those features, advanced feature, precise feature, to help nurture the decision. And this combination allows to have something very comprehensive. So from ship to shore, from vessel performance to regulation, to LNG, to offshore operation, and also the long-term partnership, because as it was said before, we are backed by GTT, our mother company, who is a long-lasting partner of the shipping industry. So yeah, we're here to help, and feel free to reach out now or later. Do not hesitate. Thank you all.
Well, thank you very much, Francois. So if you'd like to stop the screen sharing, and we'll go into the discussion session. So there's five questions in the Q&A box already. Oh, you've turned your camera off.
Yeah, sorry, wrong one.
Just a question for me to get going. So the specific innovation here. So I thought we've seen these things before on individual systems. So we've seen route planning before, we've seen ways to optimize liquefaction before, we've seen vessel performance systems before, but maybe this is the first time we've seen it as one whole model doing all of these things. Maybe for Kristian, because you've got background in shipping, is this how, this is a specific new development, do you think, so people can understand?
Yeah, I think it's hard for us to claim that we're the only ones doing this full integration, but at least I think the aspect regarding the LNG vessels is of course relatively new to the industry, and it's not many places where you get like a full integration, so that the ship modeling side, the performance side, and also the weather routing speaks well together in a system like this. I wouldn't claim that we're the only ones who does that, but at least that's one of the benefits of joining forces, is that we can integrate this much better and give much more consistent decision support to the clients related to this. And of course, as I said, the LNG side is to me new, coupling it this way.
Yeah, so how does shipping company use this in practice? Because normally different departments might have their own software, but now we've got a software model that multiple departments are using. But I guess other companies like Amazon and Walmart, everybody uses the same software system. So perhaps this is where shipping needs to go, isn't it?
I would also say there's quite a big difference when we meet clients actually on how their integration works. So some actually have very advanced IT departments where they host a lot of stuff, do a lot of modeling inside, and then use external systems through APIs to get components of that. We try to offer a full service solution, but we also allow a lot of API access to things so that it fits into the digital landscape of the operators, and that there's very different maturity levels in shipping companies when it comes to digital monitoring and management of the fleet. And as you rightly put, there's also a big difference in the departments and how to make them work together. But fundamentally, what I believe is that weather routing and performance, and now also compliance, it has to move together, because it's all the same invoice. It's all related to the fuel cost. They will increase. So these departments are forced to talk together very, very much when it comes to the daily operations. So that's why I see a definite need to unify these type of solutions.
Yeah, very good. Okay, so if we go to the questions, so we've got two people asking lots of questions. So I'm looking at your LinkedIn pages, Julio and Cedric. So Julio is Technical Director of Core Power, which does nuclear power for ships, and Cedric is a Maritime Decarbonisation Advisor with Wärtsilä, based in Nantes in France. So if you start with Julio's question, we're getting a bit technical, so maybe this is for Kristian again. So shipping does the system capture actual environmental conditions, because you can't use hindcasting? So
Actually, I'm not sure I understand the second comment, why we can't use hindcast, because that's quite standard in the industry now that you use the ship's position and hindcast weather. But fundamentally, of course, you can measure these things on board the ships. There's also very advanced equipment that can measure not only the wind speed and direction, but also wave height and wave spectrum and so forth, can be measured on board the ship. It's quite costly, and it's challenging, and I don't see that being the way that the industry goes. But fundamentally, of course, the environmental condition can easily be measured on board the ship and can be utilized just as well as it can on hindcast. But in general, I would say the advantage of utilizing hindcast is that, well, if you don't have an advanced measurement system on waves on board the ship, it's hard to detect them at nighttime. That's one thing. And the second thing is, if you use hindcast consistently across your fleet, you're quite certain it's not up to the ship's own interpretation of how the wave climate looks or how the wave periods or the split between wind-driven sea and swell. Those things are very hard for the ship to obtain with a good accuracy. So generally, the hindcast models are used. So I'm not really sure I understand the second comment. It cannot be used. Well, it is generally used, but of course, you could also get the measurements from the ship if you wanted to. It's complex and expensive, and the accuracy, unless you have really good equipment, is sometimes challenging.
Do you want to explain hindcasting? I'm sure somebody explained it to me
so
once.
Hindcast is the way of doing a wave modeling based on measurements, on live measurements. So what weather companies does, there are several weather companies that does these types of models, and it's also done internally in DNI, is simply using a global weather model at sea to determine wind speeds and wave heights and currents, seawater temperatures, and so forth. So hindcast is fundamentally just trying to create a global weather model and then determine some of these environmental factors that affects the ship. And as I said, the most dominant ones, of course, the wind speed and the wave climate and the currents.
There's another comment at the bottom, because hindcast is a guess, not a measurement. You about measuring.
And that's also fair, but I'm just also advocating that sometimes the ship is also guessing what the environmental conditions are, especially in the wave climate. It is challenging for the ship to report that accurately. As I said, they can measure it if they have very good equipment, but it's not an easy task.
Well, and the other question from Julia, I think it's for François. So this popped up when you talk about gas liquefaction, I think. So what was the 10 grams per kilowatt hour shown in the slide is the added special fuel oil consumption working at low power. I don't know if you remember what that's.
Yeah, it was the additional consumption that you have when you have too much engines working.
Okay, so that's okay. So if we go to Cedric's question from Fortsealer, so we're going back to how do your models go? So I guess that's back to Kristian.
Yeah.
How are you measuring speed in your speed power curves? Is it speed through water? How do you measure that accurately?
That's a good question, actually, because when you talk about performance of ships and how they convert power to speed, of course, it's the speed through water that we want to obtain. We have a quite advanced algorithm on our system where first of all, we like to use the ship's reported speed through waters using the speed log. They are notoriously uncertain, so we actually have an algorithm to detect whether or not you can use the ship's reported speed through water. So if that speed log works, then it's good. We can utilize that, but I'm guessing it can only be applied in 40 to 60% of the time. If that does not work, we will use the ship's speed over ground either with the AIS positions or with the ship's speed over ground through the GPS positions, and then you can correct that with the hindcast current if you want to. Again, it's not measured by the ship, but it's definitely the second best, and in some cases the best option if the speed log is not working. So yes, it's very important. The speed measurement is the single most important, of course, measurement you get, because even small deviations in speed will change the power requirements a lot. So it is very important, but you have to try to assess what was the ship's speed to water, and if the ship measures it accurately, then that's good.
Oh, and so it's the next one about the cost of reliquefaction plants. I don't know.
I think that's for you, François.
Yeah, the relic indeed. The standard one currently will consume will reliquefy 1.5 metric ton per hour at 1 megawatt. So you need to take into account, based on the efficiency of the DGs, what is the additional fuel requested to turn off the relic to generate this 1 megawatt when she's full speed. So yeah, we take it into account because it's additional consumption, but versus what the relic brings you in terms of cargo saved, that totally worth it. Sorry. So yeah, we take it into account.
Oh, very good. We've got about 5 minutes left. I've got a question I'd love to ask François, based on your background in Paris, working with startups, and I guess you're coming into shipping. But you've got a sense of where shipping is going, perhaps in 10 years. Are we going to see more and more models and a whole really, really extra sophisticated model that sits next to everybody in a shipping company, do you think?
Yeah, I think there will be more and more, and I think especially for shipping, as many other industrial use cases, the purpose is not to have a blind AI algorithm, neural networks, etc. It always has to be driven by deep industrial knowledge, such as naval architecture, such as LNG, thermodynamics, etc. You can always apply machine learning to any problem. If you do not if you're not building gray models, this will be less robust, and at some point, maybe sometimes overall very accurate, but you will lose in terms of robustness. What we're trying to do, especially with these topics, we have a big safety requirement. So we have to be sure you have to have robust things. So we need to combine it with industry knowledge. And the real challenge, in fact, for AI, because everyone can do this now, it's very almost commoditized. The idea is how you put it in production. How do you put it live with the ship? How do you refresh automatically? It's really to have an agent that supports your decision, but as much as we can is always updated versus what's happening. With the manual data or with the sensor data, let's feed those algorithms. So refine ship models, and on top of it, some layers for decision making. So as the scenario simulation Kristian presented, trying to define the optimal way, as the weather routing, what is the best route, respecting an RTA and the safety rules. On top of ship models, you need also to have some algorithm to help the decision. And those are optimization algorithms that within the group with our colleagues from OSE Engineering, we like to put in the hand of our users to really make this AI live and not a model on a machine somewhere. You need to have it live, continuously updated. The added resistance that showed for the scenario simulator, what Kristian showed, you build the scenario, but in fact, you're connected to the live assessment of the added resistance. That's the cool thing, because as soon as you are refined, you have a fine estimation of the ship consumption, the scenario behind will not be the same if you skip it. So that's why it's important to have it live, and the scenario simulator that Kristian showed is a good example. An optimization with a ship model refined with live assessment of the added resistance.
Oh, so Kristian, maybe the same question to you. So you've been involved in vessel performance perhaps longer than anybody else in the world with your colleague Jacob. But you've seen the continual evolution of this. I guess it was a sort of data analytics department for many years, like you led it yourself in Maersk, I think, and then it's got more pervasive. And now we're seeing models used in real time and supporting more different people. I mean, it's quite hard for me to imagine commercial departments using the same software as shipping departments. But Kristian, do you want to give some last thoughts about where you see this stuff going over the next 10 years?
Yeah, it's a tough question, Carl. Of course,
you're the person to answer it, I think.
No, but I of course we will see more of this thing about the system integrations and better decision support. The percentage of ships growing with these high frequency systems, or the amount of ships with high frequency systems will grow in the future, no doubt about it. But there are still many ships being delivered that's very, very analog today, right? So even though that you think that the shipping industry is very digitally mature, it's not really our impression, because you still have some very old assets or old style assets coming out. So this mix of something you can do very, very advanced with loads of data, and you could say very basic data you get from even modern ships will continue many, many years to come. I think the drive for compliance, in our opinion, has changed a lot, because this thing about the invoicing and the new reports now become basically an invoice you write to yourself, because it determines your CO2 amount and thereby the taxes of CO2, at least in the EU. But that is also something that's really going to change the industry to create more transparency, and it's going to be harder and harder to report bad numbers. So the data quality will increase. The scrutinization of data will increase. The system integration view on things will definitely increase. But the shipping industry is not a digital first mover. I think I have to say that for certain. You see new cars coming out, they very quickly adapt to the modern world. That's not how we see the shipping industry. Still still very basic designs come out. So it's a very broad span, and it's not you can't always go for the high-end solutions everywhere, because the shipping industry is very conservative, and the good means, because fundamentally they're here to transport goods from A to B and not provide data to data analysts. So it's a very diverse market, and it'll keep being diverse, I believe, in the years to come. But I think the regulatory requirements will force shipping companies, operators to to improve the data quality, and thereby allow for more these type systems that we see to work and be able to predict and help the clients to get an overview and optimize on the fuel side.
Well, I don't think we could have been doing a webinar like this 10 years ago. I think there's been a lot of change, and maybe going pretty fast, I suppose. Even if it doesn't feel like it sometimes. But
yes,
come to the end of the time now. So that's the end of the webinar. Thank you very much, Kristian and François, and best of luck with so thank you very much to our viewers. And our next webinar is on May the 7th from Opsea Log. We're going to hear a case study from the offshore support vessel sector about fuel efficiency. So enjoy the rest of your day, and thanks for joining us. Cheers. Bye-bye.
Thank you, Alex. Have a good day all. Take care.
Thanks.